Okay, let's start. All right. So we'll continue from discussing classification today. Just want to give a brief recap of what we. A typical choice is code 0, 1, right? So one choice 0, the other is 1. It doesn't have to be 0, 1. You can have anything, any way you code it. For example, another popular choice is y is equal to -1 or +1, right? Okay, or -1, 1. That's another way to popular to code it. We begin to assume 0, 1. So let's see. If y is 0, 1, what do we do? Well, this is x, right? This is y. X can be continuous, okay? If y is 0, 1, suppose this is 1, this is 0, then our data is something like this. This is typical data you have, right? Right. So when x is large, we have more ones. When x is small, we have more zeros. This is one-dimensional. That's a typical what the data looks like. So to do this problem, right, to use x to predict y, the very basic approach is still to run a linear regression. So we're going to run a linear regression like this. Okay. Now it's not going to stop at 1. It's not going to stop at 0 because we have with beta x, and if x continues, it's unlimited, right? It's unbounded by 0, 1. And what we're going to do is we're going to say, okay, we're first going to fit this. So this is our beta hat x. And then we're going to say if this beta hat x is larger than 0.5, right? This is 1/2. Okay. If it's larger than 1/2, so above. Okay. So here, if x is above this line, right, which is larger than 1/2, I'm going to declare my y hat equal to 1, right? So that's okay. So this part is y hat equal to 1. If x is smaller than this, than a straight line, I'm going to declare y hat equal to 0. That's a basic strategy of doing linear regression for the 0, 1 classification problem. This straight line is called decision boundary. Okay, decision boundary. Okay, where essentially here equal to 1, here equal to 0. Now, when y is equal to 0, 1, there's a nice way to think about what we're doing here. Remember, the model is, for the linear regression, y equal to beta x plus e. So because linear regression minimizes L2, you can think about this beta hat x as our expectation, our estimate of the expected y given x, right? Think about this one, okay? So it's a linear approximation to the CEF. This is the CEF function, right? Okay, but what is EY given x in this case when y is equal to 0, 1? Well, there are only two values to y, right? Y equal either 1 or 0. So it is equal to y equal to 1 times the probability of y equal to 1, right? Okay, given x plus 0 times the probability of y equal to 0 given x, correct? But this is just 0. So what is it equal to? Right? Right? So y equal to 0, 1, the CF, the conditional expectation function, is basically the probability of y equal to 1. Right. So therefore, if we think about this beta hat x as an estimate or approximation, linear approximation to this thing, then we can think about this beta hat x as an estimate of the probability of y equal to 1. Okay? Or approximation to it, linear approximation to it. And that's why, when beta hat x is larger than 0.5, it's like the probability is larger than 0.5, right? 50%, and we declare y equal to 1, otherwise y hat equal to 0. So one way to think about it. Now, unfortunately, this way is not very good because why? Because this beta hat x is not a proper probability, because this is the probability, but this is not a probability because this is not bounded by 0, 1. A probability should always be within 0, 1, right? So how do I make this to be within 0, 1? How can I turn this unbounded thing into something that's bounded by 0, 1? Well, I use a function to transform this beta x into between 0, 1. And the function is, what is it called? Do people remember? What is the function called? So I use a function. So from beta x, I turn it into, what is this function? Sigmoid. Okay, it's called sigmoid. And what is the sigmoid? What does it look like? E to the, so sigmoid x, let's forget about beta, right? Sigmoid x is equal to e to the x 1 over e to the x. Okay. So then, x can be unbounded, but this will always be between 0 and 1. So I'm just turning beta x into sigmoid beta x. Okay. Right. Now I can also write it this way, which is divided by ex, which is 1 over 1 plus e to the minus x, right? Okay. Right. So this is two ways of writing sigma x, sigmoid x. What is sigmoid minus x? Sigmoid minus x is equal to, look at this, right? 1 over, so sigmoid x is equal to 1 over 1 plus e to the minus x. So if it's minus x, then this is x, right? So this is equal to 1 over 1 plus e to the x. But what is this? This is simply 1 minus sigmoid x. Correct? Okay. So sigmoid has this nice, nice property that sigmoid minus x is equal to 1 minus sigmoid x. We will use this property later, okay? But this is a nice property to have. All right. So, like I said, you can think about beta hat x in linear regression. You can think about beta hat x as an estimate of e hat y equal to x. But this thing is simply a probability of y equal to 1 given x, okay? But you can think about this as, you can think about the linear model as an estimate of probability y equal to 1 given x. But this is not a very good one. This is not a very good probability model because it's not bounded by 0, 1. Right? So what I'm going to do is I'm going to, instead of assuming py given equal to y given x equal to beta x, which is more or less what the linear regression model is doing, right? You can think about it that way. Instead of doing this, I'm assuming the probability of y equal to y given x is equal to what? Equal to something between 0 and 1. Sigmoid beta x. Okay, so very simple. So beta x is unbounded. I just change it into a sigmoid beta x. Okay, something that's between 0 and 1. And that is a proper probabilistic model. Okay, so model of probability. And this is called, this model has a very familiar name that you all know, which I also talked about last time. Is basically the logistic model, okay? So this is logistic regression. Logistic regression is simply the probability of y equal to 1 is a sigmoid, is a transform of the beta x, so that we make it between 0 and 1. And it looks like, what does it look like? So instead of this beta x, right? So this beta x, I'm transforming it to look like, okay? And that is the sigmoid beta x, right? Sigmoid beta x. So that's the difference, right? This is a linear regression, least square linear regression, right? Least square linear regression. This is logistic, right? So whatever logistic does is simply transforming this linear thing into this nonlinear thing so that it's between 0 and 1. So it's a proper probabilistic model. So there's one way to look at the difference. All right, so how do we estimate the beta? Right. Okay. So in linear regression, we estimate beta by minimizing y minus beta x squared, right? We minimize this, okay, on the training sample, because that's the L2 loss function. Okay. However, when we are doing logistic regression, we have essentially a probabilistic model, right? We model the probability as this thing. So we're essentially estimating a probability, distribution. When we're estimating probability distribution, what we do is minimize KL divergence, or in other words, we're maximizing MLE, right? So we're doing maximize likelihood, okay, MLE. So to do MLE in this case, we first need to write out the likelihood. So give me 1 second. Okay, right. So we wait. Well. There we go. Okay. So to estimate the logistic regression, we need to maximize the likelihood. So we maximize, okay, this sum from I, right, from 1 to all the n data points, log probability yi given xi, right? That's what we do. Now, of course, this is a function of beta. Right? What is the log probability yi given xi? What is that? That is simply equal to two possibilities. If yi equal to 1, what is this? If y equal to 1, what is this? Expression using logistic model. Sigmoid beta xi. Okay? If y equals to 1, then this is the probability of y equal to 1 conditional x, which using the logistical model is simply sigmoid beta x. Now, if y equal to 0, what is this probability? Y minus sigmoid beta xi. Okay? So that's, so each log p is a log of either of sigmoid beta xi or log of y minus sigmoid beta xi. So everything is a function of beta. And then when we do maximum likelihood, we're simply choosing the beta, try to find the beta, then maximize this whole thing, right? Because this whole thing is a function of beta, okay? So we're just choosing beta to maximize this, and that gives us our estimate beta for logistic regression. That's how we get the beta. Now, MLE, right? Maximum likelihood MLE is also minimum KL divergence. If you remember what we said in our introduction, minimum KL divergence is the same thing as minimum cross entropy. Okay, so oftentimes when we say minimum KL divergence, we also say we are minimizing the cross entropy loss function. What is the cross entropy loss function in this case? Well, we just simply figure out what are we minimizing, right? So this is maximizing, minus it's minimizing. It's really simple. But I am going to do a little bit cosmetic change here. I'm going to say, instead of y belong to 0, 1, I'm going to change my coding a little bit. Okay. Not 0, 1. Let's do minus 1 and 1. Okay. Same thing, right? Y can be 1, minus 1, 1. Now, if we do minus 1, 1, we can write the likelihood function in an easier way, in an easier way to express that. Let's see. What is sigmoid? So, if y is equal to minus 1, 1, right? Then when y equal to 1, the probability y equal to 1 given x will still be sigmoid beta x. That's still a model. Now, when y equal to minus 1, the probability is equal to 1 minus beta x, right? However, recall, we have this property that sigma 1 minus sigmoid x is equal to sigmoid minus x. So I can write this as sigmoid minus beta x, right? But now y is minus 1. So I can write this as what? As beta x times y, right? Y is minus 1. It's minus. And here, I can also say sigmoid y, can I? Because y is plus 1, right? So I can always write, basically, if y is plus 1 minus 1, then I can always write this as a sum of log sigmoid yi times beta xi. Okay? I can always write it this way. And it's a simpler way of expressing things, right? Okay. All right. So this is called, so I'm maximizing this, which means I'm minimizing this, okay? Which means that what I'm doing is minimizing log sigmoid yi beta xi. This is essentially the cross entropy loss function, okay? That's called a cross entropy loss for logistic regression. Now, if you write it in a even easier way, because what is, let me, now sigmoid yi beta xi, what is it equal to? It's equal to 1 over, right, 1 plus e to the minus yi beta xi. Okay? And if I take the log, right, when we take the log and a minus, what happened? Then this thing, right, this, sorry, so this whole thing, come here, will be equal to log 1 plus e to the minus yi beta xi. Okay? This, ladies and gentlemen, is called a cross entropy loss, all right, for logistic regression. It's not, you don't have to remember that, but it's just an easier way to write the loss function for logistic regression. When we code y as plus 1 minus 1, it becomes much easier to write. Right? Okay. So that brings us to the next point, which is this. We can think about the logistic regression as this, okay? So this is our loss function for logistic regression when y is plus 1 minus 1. So I can think about logistic regression essentially a model. I'm going to write it this way again, right? H is a bunch of hypotheses, right? Okay. Now I'm going to say each hypothesis is a beta x. So we can think about logistic regression as a linear model as well, because this is a linear model. But instead of minimizing the L2 loss function, I am minimizing this loss function, which is called a cross entropy loss. That's another way of thinking about logistic regression, which is a linear model that minimizes this. Now let me write it even more clear, okay? I'm going to call this hx. You can think about hx just as beta x, which is our hypothesis, okay? Then this is our loss function, which I'll call it the LCE, which means cross entropy loss, is equal to log 1 plus e to the minus y times hx. Okay, so I'll give I will forget about writing x. I will not write x, right? Just h. H is beta x. Think about it. So I can write it this way. Okay. As a function, you can see that this is a function of y times h. Okay, so what happens to this y times, what is this y times h? This h is beta x. This y is plus 1 minus 1. So if we do this, what is our y hat? I'm going to say, let's think about logistic regression, right? So for logistic regression, how do we make prediction of y hat? Remember, for logistic regression, sigmoid beta x is our model of y1 given x. Okay, this is our model. So which means that we will declare y hat equal to 1 if what? If the sigmoid beta x is larger than 1/2, right? Probability larger than half. I will declare equal to 1. If it's smaller than 1/2, I can declare equal to, right? I hope you will follow me. But what is this? what is sigmoid beta x larger than 1/2? Well, it's 1 over 1 plus e to the minus beta x larger than 1/2. But you can prove, right? So this is very easy. This is equivalent to saying that beta x should be larger than 0. Okay. Remember, sorry. So, sigmoid beta x equal to 1/2 is equivalent to beta x equal to 0, because beta x is equal to, so this, from this, right, probability y equal to 1, okay, given x, is equivalent to beta x equal to log p y equal to 1 given x, p y equal to 0 given x. Okay? I hope people remember this from last time. Which means that if this is larger than 1/2, then this should be larger than 1, which means take a log, then this should be larger than 0. In other words, beta x equal to 0 is our decision boundary, okay, for logistic regression. Now, if we go back to our previous example, then you can see that for this income example, for this example, this is our decision boundary. Again, the decision boundary is a straight line. Okay, it's a straight line. Above this, y equal to 1. Beyond this, y equal to 0. If we look at a linear model, it's also a straight line, because the decision boundary for the linear regression and the decision boundary for logistic regression is both, something like this. Okay, so for logistic regression, the decision boundary is beta equal to 0. For linear regression, it's something like beta x equal to 1/2 when y is equal to 0, 1. Okay, so this is both a straight line like this. That's why logistic regression is often considered a linear model too. Although obviously the model itself for probability is nonlinear, but because it produces a linear decision boundary, it's typically considered as a linear model for classification too. Right. Now, the point is even more clear if we think about the way that I just described, which is we can think about the logistic regression essentially just a linear model, but beta x model, but we are minimizing a crisscross entropy loss. We're minimizing this loss function rather than the L2 loss, which is the linear regression. For this loss function, we have this important y times h. And as we see that the decision boundary, right? The decision boundary hx is larger than 0, okay? Then we say y hat equal to 1. Smaller than 0, we say y hat equal to -1. That's the decision we make. Now, which means that if h is larger than 0, what happens when h is larger than 0 and the y is equal to 1? In this case, our classification or our prediction is correct, right? When h is larger than 0, we will say y hat equal to 1. But the true y is also 1. So we have a correct prediction or correct classification. What happens when y equal to 1 but h is smaller than 0? In this case, our prediction is incorrect. We say our classification is incorrect. Because when h is smaller than 0, our y hat is -1. So it's incorrect. Right? What happens when y is equal to -1 and h is smaller than 0? Well, in that case, our classification is also correct. Both are -1, right? Y hat is -1. Now, when y is -1, h is smaller than 0, what is the whole thing? Is the whole thing larger than 0 or smaller than 0? Larger than 0. Okay? When y is equal to 1 and h is larger than 0, it's also larger than 0. So in other words, whenever our classification is correct, this thing is larger than 0. Whenever our classification is incorrect, this thing is smaller than 0. So we give this very nice name. We call this margin, okay? We'll call this margin. Don't ask me why we call this margin. Right? I'll explain later why. There's a reason, but I'm not going to do it today. But but margin is something that is we want to be positive, because the idea here is that if margin is positive, our classification is correct. If margin is negative, our classification is incorrect. Okay, right, so we want this to be positive. Okay, so we can think about logistic regression as a linear model that minimizes the cross entropy loss. Now, what is our old friend least square linear regression? For least square linear regression, we also have the same linear model, but we are minimizing the L2 loss function. Okay, so we're minimizing a different loss function. Now I'm going to call it, so L2. Okay, so what is L2? L2 is y minus h squared, right? Everybody familiar with this? I can also write this in terms of margin. How? Look, because y is minus 1, y is plus 1 minus 1, right? So if y is plus 1, then we have 1 minus h squared. Okay? What if y is minus 1? What happens? If y is minus 1, we have 1 plus h squared. Sorry. Correct? Right? Just minus, right? Because minus 1 minus h is really 1 plus h. So, what does that mean? Y plus 1 is 1 minus h. Y minus 1 is 1 plus h. Which means I can write this whole thing as 1 minus y h squared. I can write it this way, right? When it's plus, it's 1 minus. When it's minus, it's 1 plus. Correct? Okay, so I can also write it in terms of a margin, right? The function of the margin. All right? So I hope people are still following. But you can think about logistic regression. You can think about logistic regression as a linear model that minimizes the cross entropy loss. And you can think about the least square linear regression as also a linear model that minimizes the L2 loss function. And both are a function of the margin, okay? Y times h, when y is plus 1 minus 1. All right, okay. Now let's completely shift gear, okay? Let me ask you a very hypothetical question, which is this. If I ask you, so essentially what I'm saying here is I have two models, linear model and a logistic regression model. I can use either model for classification, okay? The difference between them is the loss function. That's all I'm saying, right? One is this loss function, one is this loss function. Then the question is why? Why do we even want this loss function? Can I choose any other loss function? Do I have any other loss function I can use for classification? What is the most natural classification you want to use for classification? Like for classification purposes, what is the simplest loss function that suppose I just want you to design a loss function yourself, okay? I give you a linear model, and just tell me, suppose I want you to use this linear model for classification purposes. What is immediately the first loss function you can think about to use for classification? I'm sure that this is not the first loss function you can think about, right? Probably not this one. What is the most natural loss function we use for classification? So if this is x2, if our x is two-dimensional, right? We can often say, okay, there are two values of y. So y can be, this dot, so maybe y can be here, right? Okay. So there are two different values of y. What I want to do is I want to separate them, right? So a linear classification model, both the logistic and the linear regression are linear classification model. A linear classification model produces a linear decision boundary. So decision boundary is a line, essentially. So for either logistic regression or linear regression model, if we're using a linear classification model, we're going to produce a straight line as our classifier, okay, our decision boundary. Something like this. And I'm going to say, okay, here, I'm going to declare everything here to be plus. I'm going to declare everything here to be, this 0, okay, circle. That's, that's a linear model for classification. So let's think about this linear model. What is the most natural loss function you want to use? What is the error you want to minimize here? You want to minimize the so I would say a natural loss function is one that minimizes the percentage of misclassified data, right? So here, look, we have 1, 2, 3, 4, 5 data points. One over 5 of them is misclassified. So this is wrong classification. Here we have, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9, So here is 2 over 9. 2 over 9 are misclassified, right? So I want to minimize the total number of misclassified points. What is the loss function that allow me to minimize the total number of misclassified or wrong prediction? What is that loss function? You have been saying forever, right? Which is 0, 1 loss, okay? 0, 1 loss is very simple. 0, 1 loss function is the simplest loss function for classification. What is the 0, 1 loss function? L, suppose this is y, this is true y, this is our y hat, right? I would simply say this is equal to 1 if they're equal, 0 if they're equal, right? If they're not equal, it's 1, right? So if I do this, then I'm minimizing the total number of ones, which is the total number of points in which they are not equal. Correct? I'm minimizing the total number of points that are not equal. So which means I'm minimizing the total number of misclassified points. That should be the simplest misclassification. So this should be the simplest loss function when we're doing classification, right? Okay? All right, so can I use this loss function? So can I use a linear model? And I'm just going to minimize this loss function. So in other words, I'm going to try many linear, like each linear model is a straight line like this, right? So I'm going to try many straight lines, okay? So maybe this line. In this line, I make, so what is the total? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5. So 15, yes, I have 15 data points here. All right? Now, out of these 15 data points, for this classifier, I make 1, 2, 3 error. So, right? So that's my error, right? That's my rate. I want to minimize that. So let me try another line. What can I do? There's really nothing I can do. Maybe like this. Okay, and I'm going to declare everything here to be plus, everything here to be 0. Circle. What is the total error rate? Well, here there's no error. Here 1 error, 2 error, 3 error, 4 error. Now I make a 4 error. So my error rate is 4 over 15, right? So I would try all the linear lines until I find the one that minimizes the total error. If I find it, that's the one, right? That's the one that minimizes the L1, 0, 1 loss, correct? And it looks like to be this one, right? Looks like this is the best we can do. I'm not sure we can do any better. Yeah, maybe, there's no way, okay? So with a straight line, this is probably the better, okay? The best one. So this is a very natural way to do classification, okay? Find out the decision boundary, then make the least amount of total errors in prediction. All right, so do we have a model like this? Remember, least square linear regression do not work like this because linear regression minimizes the L2 error, the L2 loss function. Logistic regression doesn't work like this because logistic regression minimizes the cross-entropy loss. Is there any method that minimizes the L1 loss? 0, 1 loss. Okay. So now, I hope this sort of a discussion makes clear that whenever you are using any method, any model is really 2 parts, right? We have a model. Any method is really 2 things. One thing is the model. The model tells you the functional form, and then the other is the loss function. Even the same model, if you change the loss function, that's a completely different method, right? So linear regression, least square linear regression, logistic regression, and we have something like this. And in fact, there's a name for this method, which is called the perceptron, okay? Perceptron. The perceptron model, or the perceptron method, is a linear classification method that minimizes the 0, 1 loss. So the goal is basically to try to find the line that minimizes the total number of errors. That's called a perceptron. Have you ever heard of it? Somebody, yes. Right? But most people know. And the reason why you have never heard of it, because it's not very useful in practice. Why? Because it's extremely hard to find a line that minimizes 0, 1. Because 0, 1 error function, because the loss function for 0, 1 is not very easy to minimize. And I'll show you immediately why, okay? So this is essentially a numerical issue, that this loss, remember, when you choose a loss function, the goal is to find the line or find the beta that minimize this loss function. But if this loss function is very, very hard to minimize, then this method is useless, right? It turns out the 0, 1 loss function is very hard to minimize because it looks like this, okay? Oh, before this, okay? Before we talk about what it looks like, I can write, let me replace this y as h, right? Because h is our model, okay? So h is beta x. You can think about h as beta x. So the 0, 1 loss function is, I can write it as I, whether y is not equal to h. I can write it this way, right? Okay. Now, sorry, I shouldn't say. It's not y not equal to h because h is unbounded, beta x. Y is plus 1 minus 1. So I should write whether y is equal to sine h, right? Because sine h means if h is larger than 0, then this is plus 1, right? So if y is plus 1 and h is larger than 0, ask whether y is equal to plus 1. If h is smaller than 0, then this sign means minus 1. Then I ask whether it's actually equal to the true minus 1. So I can write this way. But again, there's another way to write it, which is I can say I whether y times h again, right? This is our margin, okay? Margin is smaller than 0. Okay, I can write it this way. Why? I hope people can immediately follow because look, if h is larger than 0 and y is equal to 1, that means our classification is correct. In this case, it's larger than 0, right? When margin is positive, it's larger than 0. When larger than 0, this function is equal to 0. So, meaning when our classification is correct, our loss is 0. When our classification is incorrect, then margin is negative, which this condition is satisfied. In this case, it's 1, right? So incorrect classification, loss 1. Correct classification, loss 0. So I can write it this way too. Again, this loss function can be written in terms of this margin thing, okay? This margin. So now what I'm going to do is I'm going to plot these 3 loss functions as a function of the margin. And this is what it looks like. Where do we go? Okay, this is what it looks like. We begin with the 0, 1 loss function. So we have 3 loss functions here. The 0, 1 loss function is equal to I margin, right? Margin smaller than 0. So let's look at what this loss function looks like, right? In terms of this graph. You can see that when the margin, so the margin is here on the x, the x-axis is margin. So if the margin is smaller than 0, this loss function equal to 1, right? Equal to 1. When this margin is larger than 0, this loss function equal to 0. Okay? Does it make sense? Yes. Because the positive margin, if margin is positive, it means our classification is correct. If margin is negative, it means our classification is incorrect. So whenever we're incorrect, our loss is 1. Whenever we're correct, our loss is 0. That's the 0, 1 loss function, okay? And that's what the perceptron uses. But let's look at this thing, okay? Look at this gray line, which is the 0, 1 loss. Can you minimize this thing? Like, can you minimize this loss function? Can you find a beta to minimize this? Extremely hard to do. Why? First of all, it is discontinuous here, right? So any function that is discontinuous, it's hard to minimize at this point, right? And second of all, it's all constant. So the derivative is 0, okay? Right? So it's everywhere 0 derivative, constant, discontinuous, constant. It's impossible to do, okay? So optimization, so minimizing this loss function is almost impossible. That's why it's extremely hard to do. That's why Perceptron is not that used, all right? Now, this also gives us a reason why, even though this loss function makes a lot of sense. Okay, we're just minimizing the total number of misclassified points. We are now using it. Instead, we use a loss function that looks like here. Okay, and what is this one? This one is the logistic regression, the cross entropy loss. So if we plot this cross entropy loss function here, right, on this graph, then it looks like this one, right? You can see because why? Because it's the exponential to the negative of the margin. So the larger the margin, the smaller the thing. The smaller the margin, the more negative, the larger the loss function, right? So we have something like this. So you can think about the cross entropy loss function for logistic regression. We also call it binomial cross entropy, by the way. You can think about this cross entropy loss as an approximation to the 0-1 loss, because the 0-1 loss is very hard to optimize. Okay, right? This is hard to optimize, so I'm going to change this step function into a continuous and a smooth function that is easy to optimize. So I'm changing it into what? Into something like this, right? It preserves the essential feature, which is large here, small here, but it's continuous and differentiable. So it's good. So this is what we use for logistic regression. Now, why do we want big here, small here? Because this is negative margin, this is positive margin. Remember, positive margin means our prediction is correct. So if our prediction is correct, we don't want to have any loss, right? We don't have any penalty. We only want to penalize. We want to have large penalty if our prediction is incorrect. Here is incorrect. Here is correct. So we have a small loss here and a big loss here. So that makes a lot of sense. That is logistic regression. Okay, this is the cross entropy loss function used by logistic regression. What is the least square? What is the least square linear regression? The least square linear regression uses L2, and the L2 look like this: 1 minus margin square. What does 1 minus margin square look like? Suppose this is 1, because this is 0. The 1 minus margin square look something like this, right? Okay? On the graph you can see it, right? Something like this. Is this a good loss function for classification? No, because here all this region are correct, right? Here our margin is positive. When margin is positive, it means that our classification is true, is correct. And the linear regression penalizes, right? So even if my classification is totally correct, in linear regression, in least square linear regression, I get a very large penalty. So you can think about this case as the more correct you are, the more penalty you have to pay for least square, and that is obviously a very, very bad loss function to use. Okay? So a good loss function for classification has to be something that is only large when margin is negative, because that means our classification is incorrect, and close to 0 when margin is positive, because that means our classification is correct. Okay? So it always should look something like this. It should never go up again. Right? You should never penalize the correct classification again. So that's why least square linear regression is not good for classification. So this is just a long-winded sort of a discussion of essentially the point we made last time, which is a linear regression is now robust, right? Remember this point, right? So here, logistic regression will give you this very nice boundary, but least square linear regression will give you this very bad one boundary. And the reason why the boundary is bad is because it tries to minimize the error for these points. But these points are very correctly classified. They are very correct, but they're being penalized for being too correct almost. Okay? And so the reason underlying, right? The reason underlying this phenomena is that we have this L2 loss function that penalized very, very positive margins. But very positive margins should never be penalized. And that's why it's a bad loss function, and that leads to that's the reason behind the non-robustness to a linear model for binary classification. Okay, so this is a long-winded discussion for a pretty easy point. But the reason why I do this discussion is also to show you that you can always think about all the methods that we're going to discuss in terms of the model and the loss function. Okay, so we always define what the model looks like, and we define what the loss function is, and the loss function should always serve our specific purpose. So purpose is regression, then we use one type of loss function. Purpose classification, we should design appropriate loss function for classification tasks. Right? So loss function should be designed for the purpose at hand. And then we should pick the best model for it. If you have this kind of thinking, it's going to give you, help you go a long way in learning about all different kind of models that we're going to study. Okay? All right. So on to the next topic, right? We're still discussing binary classification, but now our y is not 0, 1. Let's take a look at a slightly different example, right? Which may not seem like classification problem at first sight, but it should, hopefully, it will show you that it is indeed a classification problem. At least you can use logistic regression model to model that. So imagine that there are 5 groups of animals. Let's say rats, okay, that are being experimented on. So the experimenter put these rats in different concentration of dangerous substance. So 1, 2, 3, 4, 5 groups of animals, and each group will have 6 rats. Okay, 6 animals in each group, and the concentration is how concentrated the dangerous chemical substance is. So this is the least concentrated. This is the most concentrated. So you can see that out of the 5 experiments, the least concentrated environment, y means how many animals died in the end. So 0 died, okay? All 6 survived. In the extreme, all 6 died, okay? Everybody dies. So our x variable here is concentration of dangerous, okay? Concentration. How concentrated our substance is. Our y variable is how many died. How many died out of 6? Okay, because we have 6 animals per group. So what is the possible values of y? Well, y can be anything from 0 to 6, right? Integer, right? 0, 1, 2, 5, 2, 6. Now, remember our problem, now we discussed the binary classification, okay? In binary classification, our y variable is 0, 1, or minus 1, 1, right? I don't want, whatever, right? So 2 values. Here we have 7 values, right? 0, 1, 2, all the way to 6. So how do I use x to predict y? Is it a regression problem, or is it a classification problem? Can we treat this as a regression problem? Can I just say y equal to, again, beta x plus c? Can I do that? X's concentration minus how many died? Can I? Again, of course you can, right? You can do anything, okay? So yes, of course you can, but it's not the best way to do it. Why? Why linear regression is not the best in this case? Because again, just like in binary classification, in binary classification, our y is either 1 or 0. And if you fit a linear regression, it can go beyond 1 and below 0. It's not bounded by 0, 1, right? Here, similarly, if our x is really continuous, and you do this linear regression, you may end up with a y hat that is larger than 6 or smaller than 0, which is obviously impossible, right? There's only 6 animals, and you can also you can also give a prediction about y hat equal to like 5.3. What does that mean, right? Okay. So for this reason, simply treat it as a regression problem may not be the best idea. Okay. So what kind of model, like how should we describe this problem? What should we do? if you think about, let's think about a probability model, okay? I'm going to do a probability model. The probability model is this. There are 6 animals, okay? And I think these 6 animals are all independent, IID, okay? Just independent, okay? They're all independent animals. I would say, suppose each animal has a probability P of dying. I do not know this probability, but suppose each animal has a probability P of dying. What is the distribution? And then let Y be the total number of animals that die in the end. What is the distribution of Y? If each animal has P probability of dying, Y is the total number of animals that die. What is the probability for, what is the distribution of Y? That should be extremely simple. What kind of distribution? Exactly, binomial distribution. Everybody familiar with binomial, right? What is suppose there's only one animal, okay? And there's a P probability of die. And then Y is a 0, 1 variable, right? Either die or not die. What distribution is that? Bernoulli, right? Okay? People, I think this should be, right? But it should be very else. So if there's a 1, that's Bernoulli. If there are n, if there are more than 1, right? It's a binomial model, okay? So it's a binomial distribution. It's a binomial distribution where we have n individuals, and each individual has P probability of equal to 1. Okay? Now, this n individual here is just equal to 6. Okay? We have 6 individuals. And this probability is the probability of dying. And the Y, which is the total amount of individuals that die out of the 6, is actually distribution. Okay? Binomial distribution with n equal to 6. And then P, is the probability of dying. Okay, so that's just basic probability, right? I'm not going to spend time on this. If you're unfamiliar, you should really refresh your probability knowledge. But this is the distribution for Y, binomial and P. Now I'm going to say, okay, so Y is binomial and P. But what is this P? This P is something I do not know. Which is, this P is the probability that Y, will die, okay? Probability of die, okay? Of individual die. Now, I'm going to say that because our X here is concentration, right? Clearly, if I want to use concentration to predict Y, then I'm going to say concentration of chemicals will affect each animal's probability of dying, right? So P should be a function of X. Okay? So I'm going to say this P is a function of X. Specifically, when X is higher, we should expect a higher probability of dying. And in the end, we'll have this one. So how do I specify this function? Can I specify this function as beta X? Can I do this? The probability of dying is beta X. Good or bad? Because it is bad, but why? Because beta X is unbounded again, right? So it's not a proper model for any probability. This probability should always be between 0 and 1. So we should not assume it's beta X. So what model should I use? What is F? How can I model this? Sigmoid beta X, okay, right? It's very simple, okay? So I want this to be bounded between 0 and 1. And if higher concentration leads to higher probability of dying, then this beta will be larger than 0, right? Larger X leads to higher probability of dying. So if we assume Y is binomial and P P is sigmoid beta X, what is this model called? What is the name for this model? This model is also called logistic regression. Okay? This is also logistic regression. It's just that it's a logistic regression. So we have really 2 cases of logistic regression, right? Previously, we were talking about logistic regression. Y is only a 0, 1 variable. And now Y is the total amount of, So right now, what is y? You can think about y as the sum, right? As the sum of many, many individual 0, 1 variables. Because we have 6 animals. You can think about each animal. For each animal, we can define like a z variable, right? We can say for each animal, z equal to 1 if the animal died, z equal to 0 if the animal survived. Then if I use x to predict z, that's a logistic regression, right? That's a classification problem that you can do with logistic regression. What is y? Y is simply the sum of zi, right? Okay, just add all the zi together. So in a group of 6 animals, if you add all the zi together, that's the total amount of people who die. So if y is the sum of 0, 1 variable, then you can also use logistic regression. Or in other words, if we do this, this is also called logistic regression. Same thing. In fact, there is a very, it looks like there are 2 different cases, but in fact, it's exactly the same case if we think about it this way. What happens when n equal to 1? What is binomial n equal to 1? When n equal to 1, binomial distribution becomes, I just said that, right? Just Bernoulli distribution, okay? Right? So when n equal to 1, binomial becomes Bernoulli. And then what is Bernoulli P? Bernoulli P is is our older friend logistic regression. So when y equal to 0, 1, so if y is just 0, 1, and I say the probability of y equal to 1 is sigmoid beta x. Now if I do this, this is our older friend logistic regression. But this logistic regression can just be thought about as y is equal to a Bernoulli of p, okay? Where the p is sigmoid beta x. Same thing, right? Exactly the same. So in other words, this whole thing is called a logistic regression. Whether n equal to 1 or n larger than 1. N equal to 1 is the classic 0, 1 case. When n is larger than 1, then y is the total number of 1 within this n. Okay? And then that's also a logistic regression. Exactly the same thing. We just have a slightly different log likelihood function. Okay? So if we have this model, binomial n pi, so pi here means p, okay, same thing. Binomial n p, p is equal to sigmoid. That's also a logistic regression. And how do I estimate this logistic regression? We write the likelihood function. And the likelihood function looks just like the 0, 1 case. Very, very similar, with the only exception that now we have n people. So we have a combination of how many possibilities in which these people die, these people do not die. And then we just time together. Okay, so you can spend some time looking at the likelihood function. It's exactly the same as before, but with a binomial modification. Okay, so now, how do we do this in R? Right. Let's try this problem. Okay, so this is our x, this is our y, this is the n. The n is like the total number each group. What we do in R is, so let's say y is the amount of animals that die, n is the total amount of animals in each group, right? And x is log concentration. So I'm just going to run a logistic regression. And here to do this in R, we use the Xiamen function. And what we need to specify, so here's x. But the y variable, instead of y, we have yn minus y. So we basically feed this matrix into as y variable. So this thing is y, which is how many animals died. 0, 1, 2, 1, 4, 6, 6. Okay, I believe that's the data. N minus 1, y is how many animals survived. So 6, 5, 2, 0, 0. Okay, right. So this is what you have on the left-hand side, and then on the right-hand side is the x. And the family is binomial, and that gives you the logistic regression. Now, let's if you have done logistic regression in R before, let's take a look at the 0, 1 case, right? Okay. Remember our income data? This is the voting data, right? Income and the voting. how do we, so here voting is 0, 1, right? Vote or not vote. How do we do this logistic regression in R? We use the geom function, vote, which is 0, 1 variable, as a function of income, regress on income, and we say family equal to binomial. Now, why do we say family equal to binomial now? I hope you understand now. Because the logistic regression is essentially a binomial distribution. When you apply to 0, 1, it's binomial with n equal to 1, which is a Bernoulli. When you apply to to more than to the sum of many 0, 1s, then it's a binomial NP. Okay. So now hope you understand why here we say family equal to binomial. Why does it mean logistic? Because logistic regression is essentially a binomial distribution. Okay, that's another way to think about it. Right? Okay. But what is GLM? What is GLM? Why it doesn't say logistic, it's a GLM. Okay? Now, when you do linear regression, least square linear regression in R, it's LM, right? Okay? Why, if you want to do y equal to beta 0 plus beta 1x, this linear regression, least square linear regression, in R, you do LM y as a function of x. Do you know what this LM means? Linear model. Okay, linear model, LM, linear model. Very good. So, why is logistic regression called a GLM? This G means generalized linear model. Now, specifically, GLM is a class of models like this. Okay. Right. So, when we talk about GLM, we are actually talking about any class of models in which Y could be thought about as a distribution whose mean variable is a function of x beta. So that's a traditional, So GLM is a generalized linear model. Is a traditional statistical from the statistics is a traditional sort of class of models concept, which is Y can be thought of as a distribution, and the distribution, its mean is a function of x prime beta. So for logistic regression, Y can be thought about as a as binomial distribution. Okay. Now for GLM, it's actually an exponential distribution, but we don't have to. You don't have to really go into details. But here, Y is a distribution whose mean, which is n pi, but pi specifically, is a function of x beta. Specifically, pi is sigmoid x prime beta. We can also write it this way. It's the same thing. Okay. Now, what is the linear regression? Least square linear regression. Remember, least square linear regression is equivalent to a normal distribution model where we assume Y is equal to n mu sigma squared, and the mu is x prime beta, right? The beta hat is similar. So this is also a GLM, right? You can also think about other things like Poisson distribution that give you the Poisson regression, which I will not talk about in this course. But the ideal of GLM is basically a more generalized linear model. So the model doesn't have to be linear in the sense that Y is not beta x. Y can be a distribution whose mean is related to beta x. That's just called a GLM, okay? It's also a traditional statistical concept. I'm not going to emphasize that in this course because I prefer, so this is one way of looking at the connection between logistic and linear regression. But this is not my preferred way. My preferred way to look at the connection between logistic and least square is the loss function that we just talked about, okay? But this is another way, right? So this is in terms of like the underlying distribution, the difference between them. This is a traditional statistical way, which I will, I mentioned this because in R, the function name is called GLM. I just hope you to understand what GLM means, okay? Generalized linear model. Okay. All right. Yeah, so, so we can do this thing, GLM, family equal to binomial, okay, estimate the how many animal died regression. And basically the estimate will tell you, look, the X, which is concentration, significantly contribute to the death probability of animals. Now, I'm going to say, so I'm going to come back to this question, which is, remember y is equal to, n is equal to 6, 6, 6, right? Okay, so n is equal to this, 6, 6, 6. Y is equal to 0, 1, 4, 6, 8. No, 6. Okay. 1, 2, 3, 4. 1, 2, 3, 4, 5. 5 groups. Right. Okay, so I just said, look, if I want to use x to predict y, I can use logistic regression, which is modeling y as a binomial distribution with p as a function of x. So this is one way. It's probably a bad idea to directly use a linear model like this, because in this case beta x can go beyond the 6 and below 0, and it can be something other than it can be 4.3, right, something like that, which is not good. However, can I actually do this? I'm going to let let q define q equal to y over n. Okay, meaning q is the observed percentage of animal that die. It's not the underlying probability; it's the observed, right? So, for example, here, what is that? 0. So for q, it's 0 because nobody died. Here it's 1 over 6. That's perceived. That's observed the percentage that died. Here it's 1 because everybody died. So q is a variable that is between 0 and 1, right? Percentage that died. Okay. Now, can I do q equal to beta x? Again, no, because beta x is not between 0 and 1. But q is between 0 and 1. But can I do this? Can I say q is equal to so q is what we see, right? Observe. So I'm going to say q is equal to sigmoid beta x. Now remember, for logistic regression, we have p equal to sigmoid beta x. This p is the underlying true probability of dying. This q is what we observe, how many people die, percentage. Q is different from p, right? Now here I'm just going to say q is equal to this. Specifically, I'm going to write it this way. Remember, there's another way to write the sigmoid, which is, I'm going to say log q 1 minus q, okay, is equal to beta x. I can do this, right? Maybe plus e, okay, because and then I'm going to define. Essentially, I'm going to let this thing be my y variable. I'm going to call it z, okay? So I'm going to run z as a y variable. I'm going to run the regression of z on x. Can I do that? Yes, I can, okay? And the reason why is, even though q is between 0 and 1, once I do this, once I do log q 1 minus q, this z becomes infinity to negative infinity to positive infinity. So I can use a linear regression, right? Okay. Now it turns out that yes, you can do this, but okay, and this beta, if you do this, your beta hat will be essentially equivalent to the beta hat from logistic regression. So if you do logistic regression, the beta hat will be exactly almost the same as this beta hat, if what? There's a condition, if. Under what circumstance the logistic regression beta hat will be almost equivalent to this beta hat, to the linear regression, like to this beta hat. By the way, this is easier to do than logistic, because we're running least square linear regression. We're running OLS, right? You can do OLS on this, and OLS is easy because it has an analytical solution. So we know what beta hat looks like. For logistic regression, we need to do minimization, right? So maximize the likelihood, or minimize, right? So we do minimization. For this one, we don't need to do anything. We already know that beta hat is, has a formula, right? Okay, inverse x prime y. So that's it. Okay. So here y will be just the z thing. Okay, z thing. So this is easier to do. The question, can I do this? Well, it turns out that under certain circumstance, the beta hat will almost be the same as the logistic. So you can basically do this. You don't have to do logistic. But the condition is what? The condition is when q looks almost exactly as p. Right? Because here, essentially, what this model is, you can think about this model essentially as q equal to sigmoid beta x, right? The logistic regression is p equal to sigmoid beta x. So they are going to give you the same beta if Q equal to P. When is Q equal to P? Or when is Q very close to P? P is the underlying probability of dying. Q is how many die, what is percentage of animal that die you observe from data. When is Q very close to P? Sorry? Because actually when sample size become very, very large, right? When n become very large, this Q goes to P, okay? In this case, in other words, if you have a large sample, you can do this. You don't have to do logical regression. You can do a linear regression like this. And it's going to give you a beta hat that's very close to the logical regression beta hat. Now, this is one way of understanding this. Another way of understanding is this logical regression is a binomial distribution. This is a linear regression. For linear regression, you can think about the linear regression as a normal distribution, right? Because the OLS estimate beta hat is the same as the beta hat of a normal linear model. So, when is binomial equal to normal? Again, when n goes to infinity, okay? So binomial, right? Binomial is a function of binomial np. When n goes to infinity, the binomial distribution approach a normal distribution. And in that case, linear regression estimate, and so the estimate here and the logical regression estimate is going to coincide. But if your sample is not large, then we have a serious problem of doing this. It can give you a lot of problems. For example, let's take a look at here. Okay? Here we only have 5 data points. And actually, I'm sorry, I should say the sample size large. I should say the n should be really large. Okay? This n should be really, really large. It's not sample size. Because when n is really large, this Q approaches this P, right? So what happens when n is small? Look at here. Out of these 6, 0 die. Out of these 6, all 6 die. So let's try the Q, okay? So here, Q equal to, so 6 die. Q is the percentage that die. So Q is equal to 1, right? Here, Q is equal to 0. Now, is the underlying P 0? No, the underlying P is, should be some constant number, just that we haven't seen any people die, right? Here, is it true that absolutely everybody would die? Not necessarily, right? But Q is equal to 6. But what if Q equal to 1? What happens to this number? 1 over 0, and take a log, right? So 1 over 0, impossible to do, okay? And then when Q equal to 0, we have log 0, impossible to do. So when Q equal to 1 or 0, this is impossible to do. Now sometimes what people would do is they cheat a little bit. They say, okay, when Q equal to 0, I'm going to plus a very small number epsilon to it. I'm going to make it 0.0001. Okay, just change it. And when Q equal to 1, I'm going to make it 0.9999, and then I can calculate the z. You can do that? Can you do that? Yes, you can. Again, because you can do all of these things. But it turns out that the result, the beta hat, will be highly sensitive to this epsilon. So if your epsilon is 0.001, or if your epsilon is 0.00001, will give you completely very different beta hat. So in other words, the beta hat is unstable, is completely unstable, depending on what the epsilon value is. So that's not a particularly good idea. You do see people doing this kind of thing in empirical research. Okay, you do see. I see this. I see many instances, many papers in which people do actually do this. They, instead of running a proper logistic regression, for whatever reason, right? For many reasons, sometimes the logistic regression you may not be able to run it, or for some reason that people decide to do this, and then they have a lot of 0 and 1. So what they do is they add epsilon, they minus epsilon, without realizing that the result is highly sensitive to this epsilon. So it's not a good idea. So that's why in small sample, if you can use logistic regression, always use logistic regression. Only in large sample, by large sample I mean when n is large. Okay, only when n is large. Okay, then you can try the linear regression estimate. All right, so you can take a look at basically my examples here. Go through them. That's exactly the point I just made. Okay. All right. So here's a comparison. This is a linear fit. Linear fit is basically y equal to p. Sorry. This p is our q. Okay, it's the q. It's the observed percentage. So if we fit the observed percentage as a beta x, then that gives us something like this, which is not a good model. But if we fit a logistic regression, that gives us this red fit. But if we do this, okay, if we do this linear regression model, and suppose we just add a tiny little bit epsilon, like a 0.001, I get this line, which looks pretty good here. Okay, it looks pretty good, right? It's not good enough, but it's okay. But like I said, this line depends highly on your epsilon. Okay, if you change epsilon, this line can change quite a bit. So it's not a good idea. However, if we use a large data set, okay, so by large I mean n is large. Okay, so now let's take a look at another data set here, cropland, right? So this data set has 3,000 counties, and in each county there are many fields that are available for cultivation. So this is like an agricultural data set in which we look at how many fields do farmer cultivate, because oftentimes farmers leave some fields empty. They don't really use them to grow crops because they think it's not worthwhile, etc. Right? So we want to study what is the how do different factors influence farmers growing crop decision. So the factor we look at here is temperature. Okay, so specifically the higher the temperature, we see that so here's the percentage cultivated. What is the percentage of fields that is being cultivated in that county? And we have 3,000 of them, right? As you can see, when temperature is cooler, more fields are cultivated. When temperature is higher and higher, we have lower and lower percentage of fields that are being cultivated in a county. Okay, so we want to model that, right? I basically want to model this relationship. Now, you can do a linear regression, okay, or maybe a polynomial regression. But like I said, the percentage is always between 0 and 1. So if you do a linear regression, you always have the risk of going beyond the boundary. So I'm going to try two things, right? So first of all, I'm going to try a logistic regression. Wait, what's going on? Looks like I jumped to the end. Sorry. Where's our problem? There we go. Okay. So this is what the data actually looks like. Different temperature for different county. In different county, there are different number of fields, and this is the number of fields out of, for example, for this county, out of 63 acres, 49 acres are cultivated. That's one way to think about it, right? So the percentage cultivated is 0.7. So that's how our data look like. Now, my goal is to predict either this one or this one, right? I can have my y equal to this, or I can have my y equal to this. If this is my y, the total number of cultivated fields, then this y is a binomial distribution I can think about, with n being the number of fields. Okay? All right, so that's what I'm going to do. Run a logistic regression with y being the cultivated fields, and the rest is uncultivated fields. And you can see that temperature has a negative effect on cultivation. Okay, on cultivation. I can also do a linear regression, which is I regress percentage cultivated, which is our Q, right? This Q is between 0 and 1. I'm going to regress that on temperature. But like I said, that's probably not the best idea because can go beyond 0, 1. So instead of that, I will do this transform. Okay, I'll transform Q into log Q minus divided by 1 minus Q, which is what I see here. Okay, log this should be Q. Log Q divided by 1 minus Q. I'm going to regress that on temperature. Okay, just like what I'm doing here. Okay, just what I'm doing here. Now let's compare the results. Right? You can see. Forget about this linear fit, because this linear fit is not a proper model. This model goes beyond 0 and 1, right? But you can see these two, okay? The red and the yellow, they almost the same. Meaning that if you use this approach, this linear regression approach, or if you use logistic regression, they give you almost exactly the same fit. And the reason is, here our n is large, okay? We have a large n, so in this case, the two approach can be pretty similar to each other. All right, so that's sort of the moral for this story. And by the way, if you look at here, I call this yellow line, I call this a linear regression or linear fit with target transform. Why do I call it that? Because remember, we talk about two kinds of transform. One is called a feature transform. Right? Feature transform is y equal to beta x plus e, but I'm going to transform this x into basis function, something like that. Okay, that's a feature transform. But if I do not transform x, if I transform y into a function of y, then that's called a target transform. For example, like log of y. Okay, it's called target transform. Here, what I'm doing is a target transform. I'm transforming q into log q divided by 1 minus q. So that's why I call it linear fit with target transform. And you can see that gives you almost the same fit as logistic. But this is only true if you have large n. Right? Okay. All right. Okay. Now on to the next topic. All right. So I discussed logistic regression applied to 0, 1 variable, and the logistic regression applied to the sum of 0, 1 variable, which is a binomial distribution. Now let's revisit an earlier question. At the beginning of introducing logistic regression and also binary classification, one important decision we need to make is we can fit the model. Okay, right? So we can fit. So the logistic regression model, is y equal to 1, conditional x is sigmoid beta x. That's again, okay, the most simplest basic formulation of logistic model, which is the probability is equal to a sigmoid. Now, again, suppose y is 0, 1. Okay, suppose y is 0, 1. Suppose I've already estimated. I have my beta hat. Okay, so sigmoid beta hat is my estimate of the probability y equal to 1. Now, given this probability, how do I decide on y hat? Shall I say y hat equal to 1 or shall I say y hat equal to 0? So far we have used the rule that if this probability is larger than 0.5, 1/2, I'm going to say y hat equal to 1. If it's smaller than 1/2, I'm going to say y hat equal to 0. That's the decision rule we have used so far, right? That gives us the decision boundary. But of course, as you have all understood now, right? So I think all of you understand now, this is subject to our purposes, okay? So what do we want to minimize? Again, that brings us to the decision theory, because whenever the y is 0, 1 and you declare y hat is 0, 1, you can make two kinds of errors. One error is false positive, the other is false negative. And if you don't differentiate between the two, meaning you don't care whether it's false positive or false negative, you just want to minimize the total error, then this is the criteria used, right? Above half, 1, below half is 0. This is called a Bayes classification. But however, if you care about which one is more important, then instead of using a 0, 1 loss function, you use you change to you redefine the loss function to give more weight to the things that you want to minimize. Okay, so let's take a look at this credit default data set. So in this data set, I have the two-dimensional x. One dimension is income, the other is balance. Balance is the essentially the amount of unpaid debt remaining on your credit card. Okay, so typically the higher the balance, meaning if a person has a lot of unpaid credit card balance, then this person is more likely to default. So here, default are people with X. People who do not end up default are, this blue thing. Okay. So our goal is to find a classifier, find a model that help to predict whether this person will default or not default. Okay. So let's do it. I'm going to. So this is our data. Okay. This is balance. This is income, and this is whether the person has defaulted or not. 0, 1. All right. The first thing I'm going to do is I'm going to do a logistic regression. Because this is a typical 0, 1 classification problem. Let's do logistic. So logistic regression, family equal to binomial, that's a logistic fit. And we can see that both balance and income are statistically significant. It's kind of surprising because just from this graph, it looks like income. Yeah, you can. I guess you can say when income is lower, then it's more likely to Is it more likely? Which one? Yeah, I can tell, right? From this graph, it looks like income doesn't really have any predictive power. But both are significant, statistically significant. Although balance is obviously a stronger effect, right? Okay. So that's our logistic regression result. All right. So now what I'm going to do is I'm going to go back to the same data, and I'm going to make predictions on each data point. Now, for each data point, I already know the true value y, right? But I'm going to make a prediction according to my estimation result to see what my y hat is on that data point, okay? So what I'm going to do is, okay, after the logistic regression, then I have a estimated probability. So based on this estimated probability, I'm going to say, if this estimated probability is larger than 0.5, right? Here, cutoff is 0.5. Cutoff is this thing, okay? If it's larger than cutoff, which is 0.5, I'm going to say y hat equal to 1. Otherwise, I'm going to say y hat equal to 0. Let's see how many errors I make, okay? What are my classification errors? This is the result. So here is the true default status. This is my predicted default status using the 0.5 cutoff. You can see that, look, for the true default, out of 9,000, how many of them? 9,600 something. Okay, so all these people are people who have not defaulted in the data. But out of all these people, I predict 38 people to default, and I predict all these people who do not default. So this 38 is my false positive, right? It's my false positive error because they should not. It should be 0, but I predict to be 1. So that's my false positive. What about my false negative? I got a lot of false negative. So out of like 300 total default case, I predict 200 of them to be not default. So I only correctly predict 100 to be default. So the false negative rate is pretty large, right? Okay. What is the total error? The total error is these two numbers add together. It's 260. Okay. I have 260 total error. Out of how many? Out of 10,000 data points. So is that good? The question is this classification good? Are you satisfied? Out of 10,000 data points, there are 260 misclassified data points. Is that good or not? Well, we can take a look, okay? 260 out of 10,000 is 2.63%. So my total error rate is 2.63. This looks like a very low error rate until you remember that in the original data, only out of 10,000 people in the original data, only 300 of them have defaulted. So the default rate is 3.33. What does that mean? That means if I have just a very stupid classifier which just predicts everybody to no default, like I don't have any model, I just predict everybody to no default. How much error do I make? 3.33. Okay, so I just do a very stupid no default. I just declare everybody no default. I only make 3.33. But if I go ahead and do a logistic regression and then make predictions, I make 2.63. Obviously, that's not good enough. So this is the first thing. The second thing is if you are working for a bank, so this is for the bank, right? So the bank needs to identify people who, the bank cares about who will default. So if you're working for a bank, do you care about the total error, or do you more care about like false positive or false negative? Which one do you care about? Do you care about false positive? False positive means people who will not default, but you think he will default. Do you care about that? Not that much, right? Not that much. It just means, okay, you're just giving one less person a credit card. Okay? But you really care about what? False negative, which is people who will actually default, but you think he or she will not default. Now that will give you a lot of loss, right? So you care about false negative. And here the false negative is huge. The false negative is 67%, right? Because, these are true default, and I predict 200, like almost two-thirds of them, I make a wrong prediction. So the false negative rate is too high. Okay, it's too high. What should I do? Suppose I still do the same logistic regression. I do not change my model. Is there any way to decrease the false negative rate? Okay. I still do logistic regression. Okay, we're not changing models. So I still have the same p hat y equal to 1, meaning the probability of default. Still same p hat. Is there any way to, so I need to, based on this p hat, I need to make prediction of y hat, right? I need to say y hat is equal to 1 or 0 based on this p hat. So far, what we have been doing is that we say if this p hat is larger than 0.5, I say it's 1. Smaller than 0.5, I say it's 0. How can I minimize the false negative rate? The answer is, now of course the fundamental answer is you need to change your loss function, but if you change your loss function, you are essentially changing your threshold, okay? This 0.5 number. So, shall we increase this number or decrease this number? If we care about false negative. Increase or decrease? You should decrease. You should make this very small, like 0.1. Why? If we do this, then you will say, basically if you lower this cutoff or threshold, if you lower this threshold, then that means you will very easily declare people to be 1, right? To default. If you very easily declare people to default, but very hard to declare people not default, you are now making false negative error, right? Because the false negative error is wrongly declare people to be not default. So false negative error is wrongly declare people to be 0, when that person is actually 1. So you want to make it very hard to declare a person 0. How do you do that? You try to predict everybody to be 1, right? If you predict everybody to be 1, then you make it very hard to predict to make a false negative error. So I'm going to decrease this threshold, okay? From 0.5 to something that is low. So let's try 0.1, okay? Cutoff is 0.1, and I do the whole thing again. You do not need to do logistic regression again because we already done logistic regression. We already have our p hat. All we are doing is changing our prediction y based on the p hat, because we are changing the threshold. Okay, so if I do that, then this is my U result. Okay, so now it looks much better. So out of 300 default cases, I wrongly predict 90. So it's already much better than before, right? So let's take a look at first of all, what is false negative rate? The false negative rate goes from 67% down to 27%. So that's a huge decrease. What is the price we pay? Because we always pay a price. The price we pay is the overall training rate goes from 2.663% now to 6%, right? So we're making more errors in total, okay? But we're decreasing the false negative error. So we're increasing the false positive and increasing the overall, but we're decreasing FNR, false negative, because that's what we care about anyway. But this 27 is still too large. I don't want to, as a credit card company, as a banking company, I don't want to have 27% of decisions I make to be wrong. Okay, when it comes to giving people credit card, so I'm going to decrease to 1%. Okay, 0.01. Okay, so as long as the probability is larger than 0.01, I'm going to say this person is going to default. I'm not going to give this person credit card. Okay, all right. So that basically means I'm going to say everybody defaults. And under very rare under very strong condition, do I classify somebody to not default? What is the result? The result is I almost got everybody correct. Okay, for those who will truly default, accept this. So now my FNR is down to 3%. Of course, that comes at a price. The price is now my total training error goes boom up, right, way up from the original 2.6% to 25%. So there's a huge increasing overall error. But if this is what I really care about, I'm probably happy, right? So that gave us this kind of curve, okay? So in this curve, we can say threshold is threshold is the like 0.5, 0.01, 0.1. As we increase our threshold, from 0 to 0.5, or you can see as we decrease from 0.5 all the way to 0, what we're doing is we're decreasing the FNR, okay, the false negative rate. But as we decrease the FNR, we always pay a price. The price is our FPR, the false positive rate, and the overall error rate will increase like this. Whether the trade-off is worthwhile depends on, number one, your goal, okay? Whether you care, which one do you really care about? Number 2 depends on where we are. So you can see that if you go from 0.5 to 0.1, we have a huge decrease in FNR, but not much price to pay. So this is probably very worthwhile. But once we go below 0.1, then we start to pay, exponentially higher price, right? As we further increase and further increase. So that's another sort of aspect that should inform your decision about what threshold you finally use. Okay, so I think we're running out of time, and next class we'll continue talking about this topic next class. Okay.